Je vais faire la présentation juste en français. On a Lucas donc aujourd'hui avec nous qui parle français. Comme vous pouvez le voir, il est à Londres en ce moment à l'Imperial College où il commence son PhD après avoir fait un passage en France. Et il va nous parler aujourd'hui des grands surveys et des méthodes appliquées à l'extraction d'informations des grands surveys. Je note aussi qu'il a un papier qui s'appelle Deep 21 et qui s'intéresse aux 21 cm, dont il ne va pas parler aujourd'hui, mais dont il pourrait parler à l'occasion si ça intéresse les gens ici. Donc, merci beaucoup. Je te laisse la parole.
Merci beaucoup pour l'introduction. Et puis, OK, je m'appelle Lucas. I'm a PhD student at Imperial College London. Sorry for I'll switch into something a little bit more comfortable.
Sure.
But this is a project that I did when I was in Paris with Ben Wandelt, Justin Outing, and Tom Charnock. So I'll be covering, it's sort of a long-winded title, but what we're trying to get at is how to boil a universe down into a couple of numbers and then what to do with them. So we'll be talking about cosmological inference in from a Bayesian perspective, but using state-of-the-art simulations and some neural networks. And we'll show you how those pieces all sort of fit together. Feel free to interrupt with any questions en français ou en anglais, ça va. But we'll pick it up from here. So as most of the people watching this, if you're a cosmologist, you know that we live in the era of high precision cosmology, which just means that we have massive and very, very sensitive surveys to be released and to be released in the next 10 years. Some of those, especially for this group, consist of some of those being Square Kilometre Array, Massive Radioastronomy Survey, and Euclid, which really seek to probe both the origin of galaxies and stars, but also the underlying statistical structure of the universe itself. We call this large-scale structure. The thing is about these surveys is that beforehand, cosmology was sort of limited by the amount of data we had, but now we almost have too much data. So the sky coverage and the depth of the surveys, so essentially the volume, these 3D images that we're picking up over Redshift, is almost too large to play with sort of at a pixel by pixel or galaxy by galaxy basis. So this brings into a question of how to interpret and mess with this data in an analysis framework. So one of the questions that I and a bunch of other researchers are asking right now is sort of how we can fit cosmological models, so models of expansion and growth of structure under gravity, whether that be Newtonian or modified. How can we fit those models and their numerical parameters, which we'll call theta in this case? How can we fit those models to the shape of the structure? Again, the structure is collections of millions and millions of pixels over different redshifts. So what we're doing here is framing sort of this inverse problem. This is from the Bayesian perspective. So given the sky that I observe, the large scale structure that we see, what is the probability of a given parameter of your model being a good descriptor of that field? And in the middle between parameter values, so if you're looking at matter content like omega m or sort of initial spread in sigma 8, this model is either a description of structure in an analytic sense, or in the case that we'll consider here, a simulator. So we know how gravity works, and we can simulate really, really detailed simulations of structure given a cosmological model by evolving a Newtonian gravitational field in an n-body simulation. So I want you to keep in mind that those two things are actually equivalent, an analytic description and a simulator, provided that you put the right physics in or the right model that you want to fit to the data. So some questions that are good to keep in mind is can we estimate distributions for these cosmological parameters? Can we come up with a posterior given just a raw overdensity field, or in this case, a cosmological survey? And can we quantify the information content of the field? And when I say this, I mean, how much information about the cosmological model does each pixel in the field tell us? And so those two are two good points to keep in mind for this discussion. So this is where we're going. It's from the density field. What are the tightest constraints using all the pixels in the field that we can get on these parameters? And this is, again, just like, you know, year one physics lab. The more data you have, intuitively, the tighter constraints you should have, because your model is more informed. There are more data points feeding into your analysis. But how can we ensure that all of these are done trackably? So this is what we'll introduce. I'm actually going to move my chat head over here, minimize you guys. This is where we introduce implicit likelihood inference, or I guess more commonly called simulation-based inference, where instead of an analytic likelihood, we have a simulator. So this simulator is able to create realizations D of your data. So in this case, it's large scale structure simulations, given some set of parameters. So you specify a couple of numerical values, and you generate a universe or your data vector from that distribution. And you can assemble this in the same way that we do any Bayesian likelihood, by calling a simulator over a prior range and constructing a posterior. So what's very cool about simulation-based inference is that you can forward simulate everything without having to derive really complicated covariance matrices. For example, if your survey has weird masks or cuts, for instance, those introduce really funky numerical values in covariance matrices, which can be a pain to derive analytically. And you can sort of forward simulate effects as you discover them, and you don't have to go back and modify your theory. The problem is, again, these simulations are massive. If you're, again, working in radioastronomy or logical structure, you know that these forward simulations even are enormous. So how do you compare a simulated universe to the one that you observe? So we're going to, this sort of brings up the need for compression. So again, this is sort of the brute force approach for for computing posteriors with a simulator instead of an analytic likelihood. So sort of going from the top left down, you observe your data, you say, hey, I think the mean is a good summary statistic to represent what this data looks like. It looks peaked at this one value. So you take the mean of that data, and then what you do is you create a simulator that can give you the same sort of shape data. You draw a bunch of different values. In this case, they're labeled theta 1 to n from your prior distribution. You generate a bunch of these simulations and you summarize them using the mean. So you just take that peak value and you compare the distance of your simulations to your observational summary statistic. So, and you sort of accept or reject according to a tunable distance parameter. So this is a hyperparameter in the problem, this epsilon that we say here. So what's very neat about this is that you can sample from arbitrary distributions, but again, this is very expensive for large simulations and wide prior ranges, especially when you don't know what the good summary statistic is to describe your simulation. So where we're going here is replacing those 1D toy examples with massive structure simulations. So these are just overdensity fields that we'll be playing with. But how do you define your summary statistic for a large scale structure? Well, the typical approach has always been to take a power spectrum. And this is actually where a lot of our M-body simulations start. We specify a power spectrum either for initial conditions or sort of background Gaussian field, and then we evolve forward to introduce nonlinearities in at smaller scales. But the thing is that when we observe large scale structure, these fields are not actually fully Gaussian, and that's actually where a lot of interesting cosmological information is stored, is in the nonlinear parts, the non-Gaussian parts of the field. So what this means is that the power spectrum is actually a lossy statistic for n-body late stage type cosmological simulations and data. Another option, which has come to light recently, and this is actually something related to that Deep 21 project that Philippe mentioned, is a supervised neural compression to summary statistics. So maybe you generate your universe according to your lambda CDM parameters, and you want to regress to those parameters and then just compare your universe to the compression of the observed universe. But again, there's no way to really verify whether or not this regression to known quantities captures all of the information of the model. So we don't know that all the pixels that consist of our that our cube or universe is consisted of are translated into this subspace, this compressed space, because again, you could regress to a scalar loss, a mean square error, but you don't necessarily know that that captures all the information that you want with respect to the model that you're fitting. And this motivates the crux of this work is an unsupervised compression technique to maximally informative summary statistics. So again, instead of regressing to some known number over a prior range, we're actually going to be regressing to arbitrary numbers that maximize the information of the model we wish to fit. So we'll get to there. And if you hadn't noticed, on the left here, I introduced some notation that will fly around a little bit later. D is our uncompressed data vector. So whenever you see D, think really, really big. And X is our compressed summary space. Whenever you see X, think small, manageable summary statistics. And again, in what I'm showing here is in simulation-based inference. If you're training your network on these simulations, you can incorporate noise and survey effects and lots of things in the forward pass. So the question then becomes, okay, well, what criterion do we wish to train the network on? What is an information maximizing loss for training this neural network? So we'll take a little detour and introduce the Fisher information, which will be helpful as a metric for our training in a little bit. So the Fisher information tells us on average how informative some data D is about a parameter theta of a distribution, in this case a likelihood that models D. So in our case, this likelihood L takes parameters theta and generates a data realization. And the Fisher information is really an expectation of the second derivative of the log of the likelihood. So this is really the curvature of the log likelihood, averaged over many realizations of D. So if your average curvature is very, very sharp, that means there's less variance in the model, and that means there's a high Fisher information. That means that the data is very informative about your parameter theta. If the Fisher information is low, this means that there's is not as informative about the theta or the model that you've chosen to model the data. So the way that this works in practice to compute Fisher information, we're going to do it for an analytic case. So again, here we've defined a likelihood. In this case, we're going to draw ND IID data points from a normal distribution. So what happens is, just like intro probability, the likelihood for all of those data points is the products of their individual likelihoods. And then if you take the log and take the second derivative, you end up with a matrix. In this case, it's with respect to the mean and the standard deviation, which are our two parameters. And so this is the Fisher information matrix for this likelihood. And what this indirectly tells us is the number of bits, or in this case, nats, we need to describe this distribution. And what's really, really neat about the Fisher formalism is that it comes with this Cramer-Rao bound, which describes that on average the minimum variance estimate for the minimum variance for an estimator of some parameter. So again, when you're looking at those posterior plots, on average, the variance is lower bounded by the Fisher information. So what this means is that if you have a likelihood, whether it be analytic or, as we'll see in a little bit, numerical, you can actually forecast how tight your model is going to be on some data. And we'll see a working example of that in a second. But just keep this in mind, that if you maximize the Fisher, you minimize the average variance of a prediction for some parameter theta. You're sort of squishing your posterior contours. All right, so now we have sort of a metric that we can then sort of start to map our large-scale structure simulations down to a much more manageable space. So again, what we're trying to do is go from a massive simulation of the universe down to a handful of numbers with the same information content as every single pixel that creates that constitutes that simulation or that observation. So this is where we're going to introduce information maximizing neural networks, which is again an arbitrary neural mapping. So this cartoon of a neural network can really be any network. What's important is how we're going to be training it. So we're going from some data distribution that's generated from some set of parameters. Again, the data is many pixels long, and in this case we've reformatted it into a cube. And then we want to squish it down into a couple of summaries. And there's actually a really nice theorem by Justin, who is also on this paper, that says if your summary space is in R2, for example, your parameter space is in R2, for example, your summary space only needs to be of size R2. So what we're going to do is we're going to figure out a way to get all of these pixels, all of the information that they tell us, down to a space that's much more manageable via a neural network. And the reason we choose a neural network is because this mapping is trainable on a numerical loss. So again, a neural network is really just a bunch of matrix multiplications down to a smaller space. And we can tune those weights according to backpropagation. So it's really, at the moment, it's the neural network itself is not super important. It's just how we're changing and warping that mapping. So what we're going to do is, again, in this X space, this R2 space, we're designing our compression, our funnel. So at the end of the funnel, we're going to have a set of numbers. In this case, it's going to be 2 numbers. And we put them into this vector X. And what we're going to do is we're going to say, okay, on average, these numbers in the summary space follow a Gaussian likelihood form. So whenever you take the covariance of the outputs of this funnel, you end up with a covariance matrix. And if you take the mean, you end up with these mu's. And every time you see a sub f, that means that it's the output of a network or some function f. And then again, we have a likelihood form in our very small subspace, which means we can compute a Fisher matrix just using the same formula we did for the little toy analytic case. We just take the log and then the second derivative with respect to the parameters. So in this case, we end up with a trace of this dot product of the mean and the covariances here. And then, so now we have a way to compute. This is at the end, this is just a matrix. And if we take the determinant of that matrix, we have a single number to train a backpropagation loss on and change our neural network weights. So what we're going to do is we're going to train until this the determinant of this matrix is maximized at a fiducial model. And so this is the whole scheme laid out. So on the left-hand side, we choose some fiducial model. We choose, let's say we choose a Planck cosmology because we like those parameters. It's sort of informed by previous surveys. We're going to plug in 2 parameters, let's say sigma 8 and omega m, and generate a universe. In this case, we'll keep the universe 2D just because it aids the training is faster. and we're going to simulate a bunch of these, again, an NS of these at a fiducial model, and then pass it through a neural network. In this case, it's convolutional because it respects a lot of the symmetries of this overdensity field. And we're going to spit out two numbers. And what we're going to do is we're going to do this 100 times, 100, 200 times in order to compute the covariance and the mean of the outputs of these networks. So every single time we pass a piece of data through the network, we compute two numbers, and we aggregate those into a mean and a covariance. And from that, we have this Fisher formula. So then for every training epoch, we can shove those through, compute the Fisher, and then adjust the weight such that this quantity here is maximized. So this is just sort of a cartoon of how the network works. And again, if you look at this Fisher formula, what we actually need here, again, there's a second derivative involved in the actual definition. We actually end up needing the derivatives of the means of the network. So that's what this comma with respect to the indexing parameters mean. So what we need to do is be able to compute a derivative, or at least a numerical derivative of this network output with respect to our parameters on the left. And what's very, very neat about this new implementation and the recent paper is that we built this entire pipeline to be completely differentiable in JAX. So essentially, we use auto differentiation to get us so at any functional point in this mapping, we can compute the gradients with respect to any other point. This is just using an inbuilt auto differentiation library. But what this means is that we can compute, once we compute these quantities out here, we can also, provided we write down the formalism for them, compute the derivatives with respect to the parameters over here. So every single aspect of this pipeline is differentiable. And what this means is that we can actually, if we write our simulator and our compression network in this way, it actually means that we're computing exact derivatives, at least up to numerical precision. So what we're going to do here, and this is also, I mean, this is sort of one of the easier cosmological problems to tackle, in that we're not looking at sort of survey specific data. We're going to generate some mock dark matter fields according to an underlying power spectrum. For this, we actually know the answer. We know how much information is contained in all of those pixels. So what we're going to be doing is verifying this pipeline on a known problem. So the first thing we'll do is train a compression on simulations of a fiducial universe. So that's our theta fid. Then we're going to simulate a new universe, pretend we observe a sky at another set of parameters, which we'll call theta target. And then once we're happy with the compression, and there'll be a little interim step on the way, we can then simulate universes over a prior. And just like that ABC step that I showed you before, we can then compress these universes down to a small summary set, which we can then compare via approximate Bayesian computation or density estimation. So there are a couple steps that we'll get through. So what we're doing here is taking our standard Eisenstein-Hugh power spectrum and generating 128 squared fields. So we're generating field images. And what we're going to do is choose a really, really horrible cosmological model to begin with. So let's say we hadn't, you were given this problem and you didn't know the Planck parameters. You knew the prior ranges for omega m and sigma a, but you didn't know what the current accepted values were. This, for any cosmologist watching, this choice of parameters should scream at you. This should freak you out, because this is way outside of current cutting edge estimates. But what we'll show is that this pipeline is actually robust to that initial choice of model. So let's say we didn't know anything about the universe. We can go through and simulate a differentiable universe. There's a plot I love to show, because we can generate, with the same random initialization, we can generate a data realization. This is our simulated universe, but we can also visualize the gradients with respect to the cosmological parameters. It sort of highlights how our derivatives, or at least up to numerical precision, are exact. So what we'll do is we follow that training pipeline. We adjust our neural network weights over a number of epochs. And what we show is that rather quickly, actually, we saturate the known theoretical field information. So this information content, which sits just below 10 to the 6, in this case, this is actually the exponential of the Shannon entropy for that distribution. This is actually the information content that's located in all 128 squared pixels. So if every single one of these pixels communicates a piece of information, the aggregate information content is represented by this dotted line. Again, this is a known problem we're solving, but with a different compression technique. So we saturate the information content at this fiducial model. Again, it's a very poor choice. We then observe the universe, so we generate a whole new new simulation, and we compress it down to a set of summaries using the same mapping. And we can actually make score estimates for the parameters using the Fisher information. So what this does actually changes that summary space and gets us closer to something that looks like omega m and sigma 8. And what this looks like on a grid at first is, for instance, it is, again, a really poor fiducial model is first chosen. Again, 0.6 and 0.6, which is really far away from anything Planck or any other surveys have measured these parameters to be. And then when we use that score estimation, we actually jump on the data. We actually jump towards a point in parameter space that's much closer to the target. So this crosshair is where we eventually want our inference to sit. So what we're illustrating here is sort of an iterative procedure. If you choose a really horrible model and measure some data, you can make an estimate, a score estimate, which jumps you to a new fiducial point, at which you can then retrain your network so that you're closer to an actual, more realistic cosmology. And what you get for free out of this network is this Fisher information. And like I said, with the Cramer-Rao bound, if you invert that Fisher matrix, you actually have a minimum variance estimate or an average variance estimate for your parameters. So if we did density estimation for this data here, our contours won't look super smooth like this ellipse that we get from the matrix, but it will be on the same order of thickness or precision, with the accuracy obviously determined by the center of the ellipse. So again, even without doing any expensive sampling over a prior, just by training the compression, we're able to get us a decent estimate for how tight the constraints are going to be from using all of those pixels compressed into a small subspace. So like I hinted at before, if your score estimates for the parameters move too much, it's in your best interest to retrain this compression at a new model, and in order to get us closer to something that's close to the target. So our target is going to be something like 0.3 and 0.78, and our score estimates get us much closer. So that's that second point here. So we'll retrain the network on simulations simulated at this point here. So once we have if you're doing this for an actual analysis and you continue making these estimates, once the estimates stay reasonably stationary in your posterior space, you sort of just sit on that mapping. That mapping will be a pretty good local estimate of the compression. So now we end up with something that's another piece of technology that we folded into this inference step. Now we're actually going to be building posterior estimates using that compression. So doing that approximate Bayesian brute force computation, except a little bit smarter, in a bit of a smarter fashion. So neural density estimation is again has the same goal of parameterizing the posterior for a set of cosmological parameters, given in this case some compressed summaries of the data, and it's proportional to this summary data likelihood. So again, P of x, x being the outputs of this neural network, of this compression, given theta, is not a known distribution. So what we want to do is come up with a parameterization for it while minimizing the number of simulations we need for traversing that prior range. So what we're going to do is use conditional masked autoregressive flows. So again, the goal here is to parameterize this guy, P of x given theta. And there's some pretty cool machinery that we can use in order to do this. So what we do is we parameterize this distribution as a product of conditional probability distributions. So if our summary vector is comprised of different components, in this case indexed by I, we can actually represent this density as a product of those individual conditional distributions. And when we put a semicolon here, we mean that this distribution is going to be parameterized by a set of neural network weights, but in a probabilistic manner. So and the way we can minimize this, again, without looking into any architecture, is once we have a parameterization chosen, all we have to do is minimize the log loss. In this case, it's just the sum of the log of these conditional probabilities. So again, the neural network here, just like in the compression step, is a somewhat arbitrary choice. The point being that we can change the mapping such that we can minimize an objective. In this case, it's minimizing this log loss. So it's the same principle as before. This is, again, it's sort of a busy plot, but the point is that we feed in in order to parameterize a conditional probability distribution, we're going to feed in both parameters and summaries. In this case, the summaries are labeled T into one end of the neural network. And the network is going to have a bunch of arbitrary connections. It can be parameterized kind of how you want, with the caveat being that the output is then a set of means and standard deviations, which governs a set of normal distributions. So what you can think of this as sort of like a neuro-Gaussian process, or a way to parameterize a higher dimensional Gaussian distribution somewhat arbitrarily. And again, this fully connected set of neurons ensures that this distribution, characterized by these parameters, are conditioned on these summaries and parameters here. And then what you do is, again, to ensure that factorization of the 1D probability distributions, you have to enforce this autoregressive property. So that just means masking the conditional distributions of the product that you end up with at the end for the loss function. Again, we're summarizing we are choosing an arbitrary mapping to parameterize our P of x given theta, our summary data likelihood. So altogether, this is a sort of a global view of the entire likelihood-free inference pipeline. So again, in this case, instead of a likelihood, we have a simulator, and this is in this case a density field simulator, or it could be n-body, or whatever your data looks like. You create a bunch of realizations that you've used to train your IMNN. Once you're happy with your compression, you take that network, and this network is now fixed. This network is just a mapping. It's just a bunch of matrices that you use to compress your data down to a couple of numbers. So what we're going to do first for the actual inference part, to build our posteriors, is draw a bunch of parameters from our prior. So this is just pairs of omega m and sigma a. Your prior can be uniform or normally distributed, however you want. You pull those values out, you plug them into the simulator, and you end up with a bunch of different density field realizations. You plug each of those into the IMNN, again, as a fixed mapping, and you end up with a set of numerical summaries. In this case, it's these x1, x2 estimates of the parameters. And what you do is you line up these pairs. So every time you've drawn an omega and a sigma 8, you lined it up with the corresponding summary in the output of the network. And then what you do is you put them into this, this flow model. This is the same thing that I showed you before. And you introduce sort of a conditional dependence in order to parameterize your summary data likelihood. So this is sort of how it all folds together once you've chosen a compression. And then what you can do is, again, is view your target universe. You put it through the same mapping. Again, this IMNN or compression network is totally fixed. Nothing's changing here. You shove it through, and you end up with a couple of you end up with your summary parameters. Summary statistics for that field. And then you can evaluate the posterior by calling this trained conditional distribution by doing sort of a sampling run. So you can do this sort of a quick MCMC. And what's very, very neat about this parameterized conditional distribution here is that once it's parameterized, once it's trained, you can draw from it for free. So it functions just as a sort of any callable probability module in Python. You can draw parameters from this, and run an MCMC to evaluate your posterior. And what's cool about this choice of parameterization for the conditional distribution is that you can then continue tightening your contours by drawing from this posterior that you've done in your initial run, drawing a set of parameters here, feeding them into the simulator, and running the whole pipeline again. And what this means is that, again, if your original prior is this entire box, this uniform box, and you end up with some initial density estimation that might look sort of like a jelly bean in the middle, you can draw from that jelly bean and end up getting much smaller contours by augmenting your training set. So you can continue minimizing this loss and then sampling for a tighter and tighter posterior distribution. Of course, this has to be done per data, per sky or data input that you observe. But there's a way to continue tightening your contours, and eventually what you end up with, as you'll see in the next bit, is a density estimation, which is our blue spot. That's very, very tight to the Fisher contours for that field. So again, here we're solving a known problem. These fields are generated according to a statistical model or power spectrum that we know. We have a formalism for computing that information content on a pixel level. We verified that our compressions maximize the information. And then we performed an inference as if we didn't know that the cosmological model. So like I showed before, we first trained, this is sort of the summary plot at the end of our paper. We first trained on a really terrible cosmological model. We retrained it much closer to where the target is after we made those estimates. And then using that compression at the better spot, we were then able to compute these density estimations. And as a verification, we also did the brute force approach, where we simulated simulations over this entire box, fed them through the network, and then accepted or rejected them. And that's sort of what you see in this magma plot, this orange and red plot. So the brighter they are, the higher the acceptance criterion. So all of the inference methods, whether it be Fisher forecasting, density estimation, or approximate Bayesian computation, all agree with the with the theory for this known problem. But what's very, very neat is sort of the expense or lack thereof of this new approach with Delphi and IMNN. So even with an optimal compression, the approximate Bayesian computation, that brute force approach, required over 12,000 simulations over that prior volume to obtain just 350 on average accepted points for each of these different fields. The density estimation approach, on the other hand, required 4,000 simulations with a couple of retraining steps and batches of 1,000. So we simplified this problem by nearly three times or reduce the number of simulations by a factor of 3 in order to produce the same quality posterior estimates. So again, optimal compression and smart sampling can reduce the numerical load of your problem, the computational load of your problem. So, and that's sort of what I wanted everyone to take away from this, is that, again, if you have optimal nonlinear compression, you can represent sort of arbitrary massive simulations with a handful of numbers. And there's, of course, some numerical, some neural network tuning that goes into it that I sort of glossed over. But again, trying this problem on known problems and then expanding it to much more complicated situations is sort of, I think, the way to go when you're doing simulation-based inference. And then density estimation also massively cuts down the number of simulations you need for inference. So again, a factor of 2 or 3 at the least. So the next steps for this problem are to apply this framework to much bigger and more detailed simulations for inference. So this means adapting that simulation pipeline to take into account an actual survey geometry. So in my case, I'm working mostly on lensing, but I have done some radio stuff, and this is applicable to anybody looking at massive surveys. And then sort of a side project that we're currently working on is using this compression network to quantify the field information in n-body simulations. So if you have a really detailed numerical simulation, we kind of want to know what bits of the cube contribute to the information content, and using these networks as a way to do that with this unsupervised loss criterion. A sneak peek of this is actually, we've built a differentiable or auto differentiable n-body code. This is a Zeldovich effect, this is a Zeldovich approximation. It's a very pixelated version of it. But again, it's the same it's the same size, the same number of pixels that we've been playing with before in the correlated fields case. And the gradients tend to be a little bit noisier, but we're actually getting close to quantifying this information with respect to a log normal field or a set of initial conditions, which should be very, very helpful in future developments. Again, most of these survey simulations will start with an n-body code and then sort of graphed observables on top of them. So I would also invite you guys, I hope there's a way to share this presentation afterward, but we have a nice set of tutorials. I have a blog post coming out on a lot of the sort of as an overview, and of course there's the paper that I invite you guys to read. And again, the code is being kept up to date, but do let me know. I'm sure you guys, if you can get my email, do let me know if you want to use this in your projects and it's not working. Be happy to discuss. I think this is it's applicable to a lot of different analyses. I'm really happy to field any questions if you have them.
Thank you very much.
Thank you.
So we have time for questions. Any question? Well, I have some questions. When you discuss the very first one, when you discuss the fact that you can reduce the number of simulations, is it when you start with very weird values of the cosmological parameters, or is it already by starting close to the expected values? What I mean is that would you need even less simulations if you start from a point much closer to the known solution? Yeah. So when I talk about the reduction, this was actually this was for this. Sorry. Wait a minute.
Can you hear me okay?
Try again.
Does this work?
Yes.
Cool. So the simulation reduction was just to create these, just to do the density estimation. The compression training is a separate set of simulations, which can be more intensive. This is just for, again, when you this is to limit the amount of brute force you need to accept and reject simulations. Again, the idea behind the compression is that maybe you have a cosmological model, like let's say it's Planck, that you like, that you can simulate a lot of simulations for that are going to be useful anyways, that you might have in a batch or on a cluster somewhere. When you're simulating over a prior, again, simulating a universe all the way over here in parameter space is not going to be very useful. So we want to limit the number of throwaway simulations that we use. So that's why we highlight the density estimation reduction, because there's a lot of simulations that don't need to be done, which can be avoided this way.
I had another question about the observations. I mean, I'm not sure I got the point about the data you use.
Okay, so in this case, this is just this is sort of an in silico experiment. So the data we observe is just data generated from another set of target parameters that we chose ad hoc. In our case, we chose Planck parameters to be the targets, and we chose that really horrible model to start with, as if we didn't know Planck, and we're looking at the actual. If Planck is the truth, which I'm not saying it is, then we pretended, again, just to verify the pipe, we pretended to observe the Planck sky, or the Planck generated.
I have maybe it's a stupid question, but so you do a compression of the information in a bunch of simulations to maximize the information, and then you compare to something that is supposed to be the data the same way. But would there be a difference in the compression? I mean, would you expect to also maximize the information if you used real data? I mean, would the comparison be fair? And you see what I mean?
Right. So this comes down to sort of model specification. So in this case, again, this is a simulation-based approach. So just like writing down a likelihood, and you know, for Planck, you write down covariance matrices, right? Because most of the information is in the power spectrum, so you can specify you specify all of the survey effects and such in the covariance matrices. So this is the same sort of idea. Instead of writing down the covariance matrices, you put in all the observational effects into the forward simulation. So if say you wanted to view the SKA sky, you'd have to incorporate both so you have the background cosmology that you're interested in, and then as the cosmology gets to you, you need to put in the Haslam map foregrounds, you need to put in all of the point sources and everything. So the whole idea, and maybe you do a foreground subtraction in that simulation before you observe the data, or before you pass it to do your inference or pass it to your network. So that's the whole idea, is the simulator can be arbitrary, which gives you a lot of flexibility for building these sort of flexible models. Because again, if your survey has a really weird geometry, it can be really difficult or almost impossible to describe that analytically or consistently in an analytic description of the likelihood. So this is super flexible. So that's actually where the Deep 21 network comes in. Again, would you want to trust the outputs of the neural network for a clean sky by itself? Probably not. But if you took that network and put it into a simulation framework where first you observe, you pass your data in, it has foregrounds and everything, then you clean it, and then you do this compression and inference, and you do that over a bunch of simulations, that is an actual robust way to, that is a Bayesian way to do that problem in a simulation way. I don't think even though I spent a lot of time building that network to the foreground separation, if you presented, you know, a resolution to some tension based on the outputs of one map or the cleaning of one map, I wouldn't believe you. I would. Again, we're looking at sort of statistically, how do all of these effects play out? And this is what this network does, is it tries to extract the information regardless of what you're doing in the simulation with respect to the model, all the way in the cosmology in the back, you know, behind.
Thanks. Maybe just one last question, which is more technical. What is JAX? What is this library? I'm sorry,
Okay.
I know about this library.
Yeah, so JAX is I don't work for them, but I'm definitely a big fan. So the JAX is the future. It's essentially a NumPy backend that is XLA compatible. So it has both XLA compatibility, which means that it can be vectorized on GPUs really efficiently, just like TensorFlow or PyTorch. And it's built on the standard NumPy library. So most of the function calls that like np.square root are the exact same, with the exception that you use the JAX library. What's very cool is that every single one of those functions, like jax.numpy.cosine of x, has an associated derivative in this library. So this is where the auto differentiation comes in. So if you build a function that, you know, is 2x squared, there you can take the auto differentiation of that and compute it for a set of numerical values. And what's the derivative of 2x squared? You end up with 4x. So the numerical outputs of that differentiated function will be as if you were evaluating 4x. So it's a really, really powerful library to write simulations and networks in, because for pipelines like this, all you need is a single the first derivative to compute a lot of interesting quantities. So I think so that's actually a big part of my PhD, is to build, or part of this, if you know François Linus, we're all part of this differentiable universe initiative, where we build these codes that are cosmological codes and simulators that are differentiable through and through. So François has this great library called JAX Cosmo, which is a bunch of power spectra and probe-like functions that have these derivatives in the back end, and that's what we use to actually compute this power spectrum. So we can differentiate through the field realization, through the power spectrum, up to the parameters that we plug in for this exact computation.
Okay, thanks. Any other question? No? Thank you again.
Thank you so much. Yeah. Happy to. Do you know how soon? I guess the YouTube link is already up, so it'll be there.
Sorry?
The YouTube link is already up.
Yes.
Cool. Yeah, I think I saw it there. Yeah. Parfait.
Merci beaucoup.
Merci beaucoup. Alors, ok, moi je vais